Hi friends, welcome to super fast revision session on linear regression, which is part of FRM Part 1's 2. These three topics are very important from exam standpoint because in recent examination there were around 4 to 5 questions in exam. So in this session we will cover three topics. So first is reading number 7 linear regression, second is reading number 8 linear regression for explanatory variables, and then reading number 9 is the regression diagnostics. So these three readings are important, very basic. If you understand these readings properly, you will be able to score all questions in examination. Now here, because it's a revision session, I'm expecting you to know all these concepts beforehand. So I'm not going to give you any background explanations of the concepts, and we will keep our focus on exam important area, exam testable area. Now, first of all, reading number 7, linear regression. So this is a very basic reading. We'll start with the basic meaning of linear regression, and then we will move into our calculations. So we all know the equation of linear regression. It starts with the y is equal to alpha plus beta x1 or x simply. You can also take beta 1 x1 or beta x. And then we also add the error term, but for now we will keep error term on hold. We will discuss error term later. We will keep our focus on y is equal to alpha plus beta x. So as we all know, y is the dependent variable or the explained variable. The dependent variable or the explained variable. On the other hand, x1 or x is the explanatory variable or independent variable. So x explains the value of y, and this is the linear regression equation. So here, this x is observed value, which will be given in examination. You can't calculate x. Okay, so if I have to give the simplest example, if student prepares for 800 hours for FRM examination, what will be his score? Okay, so x is the number of hours of preparation, y is the score, and we do this calculation with the help of alpha and beta. X is observed, y is calculated, so we don't have to bother about these two values, so y and x. So we have to only focus on alpha and beta, and we have to do the calculation of alpha and beta. This is our goal of this particular reading, linear regression. Now here there are multiple methodologies available for the calculation of the alpha and beta. Alpha is known as the intercept, beta is known as the slope coefficient or the regression coefficient. So to calculate alpha and beta out of multiple methodologies, we have to focus on only one methodology, which is known as the OLS, ordinary least squares method. This method has predefined rules. You have to apply those rules and you have to do the calculation. That's it, as simple as that. Now here, the error term is the residual or the left out part, the part which is not explained by x while determining the y is known as the error term, right? So we'll discuss error term in detail later, not here. So let's start with the introduction. In the introduction, we have the exam score, same example which we saw here. Now here, the alpha, beta and number of hours of preparation. Okay, so this is the Falcon's book we are using here. So if you are using Falcon's book, well and good, best for you. If you are using any other study material, you can follow that as well. So you will find a lot of things different here. So not in concept, but the way things are explained or the details. So Falcon's notes are much more detailed compared to any other notes. Now here, so you want to bother about the details. You can focus on the concepts. Now here, this is our linear regression equation, and then this is the example. So 20. Assume the 20 is intercept, 0.12 is slope coefficient, and 500 hours of preparation means a student is likely to score 80 in examination. Now, first steps in linear regression. So first we'll state the problem, then we will select the variables meaning exam scores are affected by multiple variables, multiple factors, one of which is number of hours of preparation, second is how many questions you solve, third is how many mock tests you give, fourth is how confident you are in examination while sitting for the examination. There are four factors. Maybe if we consider first three only, number of hours of preparation, then we have say number of mock tests and number of questions solved. If we consider these three variables to determine the exam score, so this is a variable selection. You have to select these variables and identify these variables. Then we will collect the historical data. So we will take the historical data, apply a regression model or the concepts of regression model on that, and then we will find out alpha, beta, and then we will find the exam score. So data collection is the historical data collection. Then model specification. We have to specify the model. Are we going to select 3 variables, 2 variables, or 1 variable? So in this session, we will focus on the 1 variable. In the next reading, we will focus on the more than 1 variable. So here then we have the model fitting. Model fitting means how good the x is predictor of y. Okay, so this is the meaning of model fitting. So we'll try to fit the model. We will see how good the model is, how good the explanation is provided by x for the y. So this is the basic meaning. Then we will do the assumptions checking. Assumption checking is we will use some assumptions for linear regression, and then we will check those assumptions, and then we will do the forecasting. Forecasting is not generally the part of FRM curriculum, but in examination you may get the question of forecasting. Forecasting is nothing but Alpha will be provided to you, beta will be provided to you, x will be provided to you, and then graph will ask you what should be the value of y. Okay, so this is how this forecasting works. So these values should be provided to you, or if the question is slightly advanced, then the information required for alpha and beta calculation will be provided to you. So you don't have to worry about it. These calculations are very simple and straightforward. Now linear regression versus non-linear regression equation. Okay, so what is mean by linear versus non-linear? Now linear equation looks like this. So y is equal to alpha plus beta x. If I give you the equation alpha plus beta x square plus error term is still the linear regression. If I do this, still the linear regression. This means we are not concerned with x. We have to focus on beta to identify the equation or the model is linear regression or non-linear regression. If the beta enters into model multiplicatively, like in this case, so beta multiplied by x1, then we will call this as a linear regression. If beta enters into model in any other mode, like this, or like this, or like this, maybe beta here, and then one more coefficient here. So this is the non-linear. So I have to remember this for the examination purpose. Remember, the linear regression equation is the one in which beta enters into model multiplicatively with x. There is only one beta coefficient. You have to remember this beta coefficient for every one explanatory variable. So this is very important. Now, to become a linear regression equation, you have to remember these. These are the three essential properties. So first of all, the relationship between the dependent and the independent variable must be linear in unknown coefficients. Unknown means we have to find out or calculate the beta coefficients. If beta coefficients are known to you, then this is not the linear regression equation. This is not the regression itself. Okay. So for example, if you want to find out what is the cost of say chocolates you want to purchase, there is no alpha. Alpha we will assume as 0. One chocolate costs 10. Okay, so this is your beta multiplied by you buy 100 chocolates. So 100 multiplied by 10 is 1000. This is your cost for buying 100 chocolates. Now here, this beta is already known. So this is not the linear regression. So you have to identify or calculate beta to make this a linear regression. So this should be unknown. So I have to focus on this particular word. Model must have single unknown coefficient. So only one unknown coefficient multiplied by single explanatory variable as we discussed. Then errors must be additive. Okay, so errors must be additive as in you have to see the y is equal to alpha plus beta x1 plus error term. This is the error, should be additive. And variance of error term must not depend on observed data. This is the meaning of this statement. You have to remember this meaning. Your observed data means explanatory variable. X should not be able to predict or regress with the error term. Okay, so if you perform the regression analysis of error term and explanatory variable, you should not get any result. So this is the meaning of the statement. Then last is all the explanatory variable must be observable. All the explanatory variable must be observable. The meaning of this statement is very simple. If I have the data of say, again, we take the same example, number of hours of preparation versus the exam score. Okay, so how you will score depending on how many hours you prepare. If there is one student who comes to me and says, okay, I studied for 50,000 hours, what will be my exam score? In this case, that particular model will not be able to perform because the condition is all the explanatory variable must be observable. So these variables should be observable. So out of the observed values and out of the observed conditions, it should exist. So maybe if someone says 200 hours, 300 hours, 500 hours, 1000 hours, like that. Then we have the explanatory variable that can be continuous, discrete, or the function of one or more variables like this. So x is equal to x1 plus x2 is also the linear regression. You have to remember this. Okay? So we already discussed this. Then we have the ordinary least squares method. In ordinary least squares method, our goal is to identify or calculate the alpha and beta. X is the observed error term. You don't have to bother about it. This is provided in the examination. It is not possible for you to calculate the error term. Please remember this. Then y we will calculate. So here in the OLS method, the formula is very simple. In step 1, what you have to do? You will be provided with the information like this. So covariance of x, y, variance of x, and then you will be provided with the bar, y bar, and these informations will be provided to you. Now, in step 1, you have to first find out the beta. So this is the same beta formula which we use in the CAPM, which we use in the hedge ratio. Exactly same formula. So covariance of xy divided by variance of x. You have to do this, you will get the beta. Now, in this equation, y is equal to alpha plus beta x. In this equation, we already got the beta. Now here, for x and for y, just replace x bar is equal to alpha plus this beta is already known to you. Now you have calculated it, and then x becomes the x bar. So x bar's value is provided, y bar's value is provided. You did the calculation of beta using these two values, that is the covariance and the variance. And obviously, you are smart enough to solve for the correlation, intercept. Okay. Now the parameter estimation. So here we are going to find out this particular model. Just focus on this. So y hat is equal to alpha hat plus beta hat into. So here we have to just understand why are we saying the parameter estimation? Because as in any statistics, we are going to use the sample data and not the population data for the revision. And with the help of the sample data and the model built on sample data, which will be y hat is equal to alpha hat plus beta hat multiplied by x. Using this model, we will try to predict the parameters of population. And that's why we call this as parameter estimation, because we are trying to estimate the parameters of population. So estimate is the keyword here. Remember, parameters are for population, estimates are for sample. This is the only difference between the parameter and the estimate. What estimates the population's parameter is known as the estimator. This is what you have to remember. Now, calculation of beta is correlation coefficient. So here we have the basic formula. You have to focus on this particular formula. This is the alternate formula. So covariance of xy divided by variance of x is equal to correlation correlation of xy multiplied by SD of x, SD of y divided by SD of x. So these are the two formulas, and chances are you will get either of these formulas in examination. So not the formulas, so information required to calculate the beta using this formula. So maybe you may get the correlation SD of x, SD of y, then you have to use this particular formula. If you are provided with the information which is the variance of xy and covariance of xy and variance of x, then you have to use this particular formula. So you have to simply use the formula here. We have this particular table. This table is for your explanation when you are studying everything in detail. I wanted every student to know things in detail. That is how calculations are going on. So that's why this table is provided. This table is not at all important for examination. In examination, you will be provided with these values like this. Then, so this is variance of x. This is covariance of x, y, and not covariance. You have to divide it by n. Simply the x minus x bar square, y minus y bar, x minus x bar. Okay, and these are the values. You have to divide it by n. After dividing it by n, get your beta. So once you get your beta, then you have to find out the intercept. Finding intercept is very easy. You already have y mean and the x mean. So simply use this y mean beta, which is calculated from here, and then x mean. X mean is this. Then simply put this and you will get alpha is equal to 8.04. Now once you know the alpha, once you know the beta, x is the observed, you will be able to calculate y, and this is our final equation. Okay. Then we have the error term and sum of squared errors. So as I said, you will see like calculations are provided here, but these calculations are not at all important for examination. So you have to only focus on the equation. So equation goes like y is equal to alpha plus beta x plus minus error term. So what is this error term? So obviously when we will try to find out or predict or model our data with help of this, x is not going to find out y with accuracy. Okay, so there will be some error because of obviously like inherent nature of this model. So these errors are captured by error term. Now how to capture the errors? So you have to only focus on these values. So first of all, y actual, whatever is the actual value. For example, again of number of hours prepared and actual exam score. So this is actual exam score. This is predicted exam score based on number of hours of preparation using our model. These are model values, and there is difference between the actual value and the model value. So if you calculate y minus y hat, that is actual value and the predicted value. This is your residual. If you calculate the square of this, you will get residual square, and this is how the ordinary least square term comes into the picture. And for the explained square, you have to simply take the y hat minus y bar square, and you will get the explained squares. So again, as I said, all these values will be provided to you in the examination. Our focus is on, like, we have to only focus on these values, okay? And then we have summation of error term square, okay, and then this is the value. So 433.87, right, provided in exam. You try to calculate it. Now, the aim of the OLS, this is the meaning of OLS. So aim of the OLS regression is to reduce the sum of squared residuals. Reduce this particular value. Error is that term which says, okay, this much error is left in your model. This much part of this particular relationship between the y and x is not explained by x using this particular model. And the aim is to reduce this error as much as possible. Then we have the concept of R square, explained and unexplained variance. So this is a table. So table is in the graph. Check this graph. Then we have the TSS, total variance. So which is known as the TSS, total variance between the terms. Okay, so y minus y bar. The total variance. Again, this is analogous to the variance we calculate. So what is the formula for the variance? Variance is equal to summation of x minus y. Summation of x minus x bar, or if we use the term y, summation of y minus y bar square divided by n minus 1 for the sample divided by n for the population. So this is same term, total variance. Then we have the explained variance. Explained variance means the whatever the model is able to explain, that is y hat minus y. Simply we are replacing this y with y hat, that is a predicted value of y, and this becomes our ESS, and then RSS is whatever is not explained by this particular model. Now, obviously, explained part of the variance, residual part of the variance becomes, if you add it, it becomes a total part of the variance or total variance. Now here, R square is ESS upon TS. R square is ESS upon TS. Explained part divided by total part. Okay, so part of variance. So explained variance divided by total variance. Explained variance divided by total variance is the R square. Or the alternate formula is 1 minus, this is simple mathematics. 1 minus RSS divided by TS. RSS divided by TS. Simple. Right. Then we have the R square using the previous example. So where our total sum of squares, TSS was 927.69, then ESS was the 493.82. So explained part, or the R square is 53. So this is how to calculate the R square. So what is the R square? R square is the coefficient of determination. This shows, or R square provides us, what is the explanatory power of this model, what is the value of this model. So 53% part or 53% variance is explained by this particular model. So maybe to improve the explanation part or coefficient of determination, you may need to add some additional variable if required, or if you have only one variable to predict or determine, then 53% is pretty low, not so high. So you have to remember this, R square is the coefficient of determination of the explanatory power of this particular model. Then important note for the R square in examination. Now remember, if you take the under root of R square, if you do this, if you are provided with the coefficient of determination from the linear regression, and if you take the under root of this, you will get the correlation of x and y. Now, this particular part or property is only applicable for linear regression with one variable. If there are multiple variables and you are provided with the R squares information, which is not that useful, we will use adjusted R square in that. So if you are provided with the R square, you can't simply take the under root and calculate the coefficient or say correlation coefficient. Okay. So this is very important note for the examination. You may get theory question on this. Now next, dummy variables. How to treat the dummy variable? You all know what is the purpose of dummy variable. There are some informations which cannot be used as a numerical value. For example, male female, maybe for male working or studying for 800 hours works in different manner compared to for female. So how to fit this particular value, male or female? How to accommodate this information? So for male, we will put 1, for female we will put 0. So now 1 and 0 are the numerical informations or numerical values, and it becomes a numerical variable, and this is the only way to introduce the categorical variable, the factor variable, the male, female, pass, fail, work status, working, full-time student. These type of information which are of the categorical nature and not the numerical nature can only be introduced with the help of dummy variable. So in dummy variable, what do you need to know? What is the important area here? So the only thing you need to know here is if you want to introduce two factors or two categories, for example, say male, female, and for male 1 and for female. If you want to introduce these two categories, then you have to only use one dummy variable in B2, maybe in B3, can be anything. We will call this as maybe this particular variable will be considered as a D1. So D1, D2 like that. So only one dummy variable is used for two categories, which will, so one of, like if you assume this as a dummy variable for male, then the female's impact is captured by the intercept. Female's part is captured by the intercept. Okay, so this is very important, and if you know this is more than enough for examination. The proper dummy variable equation, linear regression equation with dummy variable like this, and the rest of the part is captured by intercept. So for two categories, we'll use one dummy variable. For 12 months, we will use 11 dummy variables. For 4 quarters, we will use 3 dummy variables. This is the most important part of this dummy variable. Now, properties of OLS estimator. So first of all, shocks are mean 0. You have to remember this, understand this, and not shocks are mean 0. Shocks are mean 0. Now, shocks are mean 0 means if these are conditional upon x. So if you take the mean of error term conditional upon x, you will get answer 0. And this particular property is very important. So this from exam standpoint, from the exam perspective. Now here, to do this, okay, to make sure the shocks are mean 0, this is the property of linear regression. You have to make sure few things. So first of all, you can't treat this property in model. You can't do anything with model to make sure the shocks are mean 0. We have to follow certain procedures here, and these procedures are, first of all, make sure there is no sample selection bias or survivorship bias. Sample selection or the survivorship bias means whenever you are taking these samples, you should not take only survivor samples. For example, we have the hedge fund, and we are taking the or doing the analysis of average income or average returns produced by the hedge funds in India. So in that case, only surviving hedge funds generally report their returns, because we can't go to their office and ask for their returns. And whoever are performing good, they will report to us. Whoever are not performing good, they won't report. So this is survivorship bias. Survivorship bias is the first way. You have to make sure whenever you are doing or collecting the data. Okay, so the first part is covered or managed by data generation and not in the model. This is the important part. Then we have simultaneity bias. This means you should not derive x and y simultaneously, or you should not determine x and y simultaneously. X and y should not be a function of each other. This is very important. Then we have the omitted variable bias. You should not exclude the important variable. Then attenuation bias. Attenuation bias is when the independent variable measured with the error, which results into inconsistent parameter estimation. So attenuation bias results into estimated slope which is flatter than 2 relationship. This is what you need to remember for examination. There is no alternative. Okay, so these are all the properties you have to remember. So this was the first property. What is the first property? Shocks are mean 0. We can't correct it in the model, so we can't treat model in certain manner, which makes sure the shocks are mean 0. So the only way out is you have to follow certain procedure in data generation process. In data generation process, we will ensure all these properties or all these measures are taken care of. There is no sample selection bias or survivorship bias, simultaneity bias, omitted variable bias, and attenuation bias. Then we have the data realization from IID random variables. So that is all the x and y are IID, independent and identically distributed. This is very simple assumption. Independent means not related to, independent as in x and y can happen independently, and identically distributed means the distribution should be similar. Okay. Then we have variance of x is greater than 0. Again, x, that is the variance of x is positive. This is again the condition you have to remember. Again, I won't be able to give the explanation here because this is a revision session, or else the revision session will extend to say 2 hours or 3 hours. It will become regular session. Then we have the variance of error term. Shocks are finite and constant. So error term should be finite and constant. You have to remember this. Then we have the no large outliers property. So you have to make sure there are no large outliers. Now, implications of OLS assumptions. Here we have some correction. Read this. And first of all, estimators are unbiased, and two estimators are jointly and normally distributed. So these are the two implications. Then next is the properties of OLS estimator and their sampling distribution. So this is the basic part. Then we have the hypothesis testing part. Hypothesis testing. Now remember, recall our equation. Y is equal to alpha plus beta x. Now here we don't bother about hypothesis testing of intercept. Why? Even if the intercept is 0, our model is still relevant. Y is equal to alpha plus beta x1. Even if this is 0, x will be able to predict y, right? But what if this particular beta is 0 and we performed calculation in wrong manner and we got some value for it? That's the problem. In reality, beta is 0, meaning there is no relationship between the x and y. X is not the predictor of y. Okay, so x is not the explanatory factor of y. So if this is happening and we somehow calculate beta and get the value of beta, say 0.2, but what if in reality this particular value is 0? And this is the purpose of hypothesis testing. We don't perform hypothesis testing for, we can perform hypothesis testing for intercept alpha, but we don't because it doesn't affect our model directly. On the other hand, if beta is 0, then it will affect our model extensively. Our model is completely useless if the beta is 0. And that's why we have to make sure that beta is not equal to 0, and that's why the null hypothesis is that the beta is equal to 0 and alternate is beta not equal to 0. Okay, so this is our hypothesis testing setup. Now here our objective is to reject null, and if the null is rejected means beta is not equal to 0, right? So beta is not equal to 0 means beta have some value. If beta have some value means model is significant or model is useful, and this particular process means the beta is statistically significant for our model. So in short, we say this as beta is statistically significant if we are able to reject the null hypothesis. This is what you need to remember. Now here we have our data. So there are three methodologies available. So t-stat method, confidence interval method, p-value method. So here all the values will be provided to you. So like beta, you need beta here. So what is the beta from your model? Standard error will be provided to you in the examination, so you don't have to worry about standard error. So simply take beta divided by standard error and get your t-stat. Once you get your t-stat, simply if your t-stat is greater than t critical, slope is statistically, or the beta is statistically significant, and reject null. Second, so you have to remember only this much part. Okay, so you have to remember the properties. So reject null is our objective. We will reject null if we are using the t-stat method. We will reject null if the t-stat is greater than t critical. Remember this. Then if we are using the confidence interval method, question is like that, then you have to make sure if the 0 is not in that particular confidence interval, like here you can see we build the confidence interval and this particular 0 is not in between 0.236 and 1.06. obviously this is common sense, right? So in this case also null is rejected, slope is statistically significant, and this is what we want to make sure our model is relevant. And the last is if the p-value is less than the significance level. So here you can see the p-value is less than significance level. Significance level here was the 95%, 5%. What? 95% confidence level. Important part or important note here is, in examination you may get a theoretical question, and in theoretical question you have to look for these particular properties. So t-stat is very high, reject null hypothesis. P-value very low, reject null hypothesis. Like this. This statement is important. In examination, this statement will be very useful. Then we have the regression with multiple explanatory variables. In this, first of all, we are starting with the multiple explanatory variables. So in previous session, we used only one explanatory variable. So y is equal to alpha plus beta x. Now here we will introduce multiple variables. Okay, fine. So now we don't have to bother about finding out the betas here, because betas will be given in the examination. It is not practically possible to calculate beta 1, beta 2, beta 3 examination, which it requires a lot of like computation. So computation won't be covered in the examination. So now in this chapter, the important part is the assumptions and the interpretation of the slope coefficient. In multiple explanatory variables, the slopes are known as the partial slope coefficient, and this is what you need to remember. Now here, so first of all, assumption in multiple explanatory variable, and this particular first assumption is applicable only for the multiple regression models. So explanatory variables are not perfectly linearly correlated. This is the assumption only applicable for multiple explanatory variable. And set 2 of assumption, this is set 1 of assumption, it is not required here, this is only one assumption. Now set 2 of assumption is applicable for both regression models, so one variable and the multiple variables. Now all the variables must have positive variance. First, error term is assumed to have mean 0. Again, we already discussed this. Random variables are assumed to be IID, X, Y are IID, independent and identically distributed. Then we have next, no large outliers, constant variance for all explanatory variables. Homoscedasticity. Like this is the meaning of the term. Now interpretation of regression coefficient or the partial regression coefficient. Now here understand. When we discuss the y is equal to alpha plus beta x, means the one variable equation. This means if the beta is, whatever is the beta. So if beta is 1, then this means if x increases by 1 unit, y will increase by 1 unit. If beta is minus 1, this means if x increases by 1 unit, beta will decrease, y will decrease by 1 unit. I'll just write it down. Y is equal to alpha plus beta x. Now here, if this is the beta, if x increases by 1 unit, then y will get impacted by x multiplied by beta. Okay, so what is the impact here? So beta is 1 in our example. So if x increases by 1 unit, then y will increase by x multiplied by 1, obviously by 1 unit. If the beta is minus 1, if x increases by 1 unit, then y will decrease by 1 unit. So this is the meaning of this particular slope coefficient when we are dealing with the one variable. On the other hand, when we are dealing with the multiple variables and the equation is y is equal to alpha plus beta x, beta 1 x1 plus beta 2 x2. So in this particular case, this particular slope coefficient means the impact on y by changing x and keeping other variables constant. You have to keep other variables constant. And that's why this particular beta, what is the meaning? If someone asks you what is the meaning of beta or what is the significance of beta? So beta is the impact on y per unit change in x by keeping all the other explanatory variables constant. Remember, the word is constant, not zero. Our trick student. The statement goes like the meaning of slope coefficient. So partial slope coefficient in multiple explanatory variable is called as partial slope coefficient because this is the statement. Which one of the following statement is true and false? This is the format of the question, and I am giving you this statement and see how statement goes. The beta, in multiple explanatory variable regression equation, the beta is known as the partial slope coefficient because beta is per unit change in y for the change in x given all the other variables 0 or keeping all the other variables 0. This is wrong statement. The correct statement is by keeping all the other variables constant. So you have to look for this particular word. This is a very important word here, and this is the meaning of the partial slope coefficient. This is the partial slope coefficient. You have to read it. Okay, then we have this particular setup. So in this setup, we have assume you have multiple explanatory variable equation and you got these values, and similar type of values may be provided in the examination. Okay, so I will just give you the basic explanation. What is this particular question? So here in this model, you are seeing YouTube, Facebook, newspaper. So assumption is, so as a Falcon event, we are putting money in Facebook ads, YouTube ads, and newspaper ads, and we are trying to identify what is the impact on sales. So we got our coefficients like this. So this is our intercept. This intercept means, the meaning of intercept is if x is 0, that is we don't put any money in any ad. We don't pay for add. So add is 0. So all the x are 0. Even in that case, we will get this much revenue. Then this is coefficient or beta for this particular variable. Call this as x1. If this is the x2, then this is the beta for this variable. And if this is the x3, then this is the beta. And final model is like this, using the same values. So if you are provided with this particular table in examination, always look for coefficients, and coefficients are treated like this. Intercept, intercept goes here, beta, 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 respective betas of each variable. Graph will provide you specific information on this. Okay, so 10,000 spent on YouTube ads, say 15,000 spent on Facebook ads, and say 20,000 spent on newspaper ads. So what should be the sales? Like this. So you have to simply use these values and find out the answer. Then we have the goodness of fit. So here our R square is not very important. Okay, our R square is not useful in case of multiple explanatory variable, because with every added variable R square will either be 0 or it will increase. Okay, so if you consider 100 variables into the model, R will increase and R is likely to increase, and we want some model, because our objective is to keep sure or make sure our model is like that. So all the important variables are included and all the unnecessary variables are excluded from our model. This is our objective. Now here, because this is our objective, we wanted some particular measure, which particular measure is known as R adjusted square. So we wanted some particular measure which gives us the proper information that if we should add this particular variable or not. Because if we use the R square, then when you add extra variable, R square will increase or it will be constant. So R square is not giving us any additional information. So we went for adjusted R square. Adjusted R square has a particular formula. This particular formula you must remember. So 1 minus n minus 1 divided by n minus k minus 1 bracket 1 minus R square. Here the k is number of explanatory variables, n is number of observations, that is, and n minus 1 is the degrees of freedom. Again, n minus k minus 1 is the degrees of freedom, right? So 1 minus R square, here this R square is your coefficient of determination. So we have to use these values. You have to remember, if the variable is not important, because of the setup of this formula, if the variable is not important, if you add that variable into the model, R adjusted square will decline. If the R adjusted square declines from the previous model, and we can give the take the example of, say we have two explanatory model, okay, two variable model. So where we have two variable, we want to introduce the third model. Our current R adjusted square is 76%. If we add third variable and our R adjusted square goes to say 74%, so we should not include that particular variable, exclude that variable, check for the next variable, like that. Okay, now here again we have the explanation for that particular part. Here very important question, can R square be negative? No, R square cannot be negative. Second question, can adjusted R square be negative? Yes, adjusted R square can be negative when the R square is very low, first condition, and the added variable or the added variable, extra variable which we are adding into the model is not the explanatory of the independent variable. This is what you need to remember. Then we have the joint hypothesis testing, and in this joint hypothesis testing, this is for H0 is equal to all the beta coefficients equal to 0 versus at least one of the coefficient is not equal to 0, and this is the hypothesis testing setup. So H0 means null hypothesis, all the beta coefficient is equal to 0. So what are we checking here? We want to make sure all the beta coefficients are not equal to 0. If one of them is 0, then also our model is useful. If all are 0, then model is completely useless, right? So this is what we are doing here in the joint hypothesis. First option is you can always go for the individual hypothesis testing, individual coefficients hypothesis testing. But here we prefer joint hypothesis testing. Here the null is like this, all the beta coefficients. I'm repeating one thing again and again so that it sticks in your mind. So it is not my problem, okay? It is for you. So whenever I'm repeating something, focus on that. So beta, all the beta coefficients is equal to 0 is the null hypothesis. At least one of the coefficient is not equal to 0 is alternate hypothesis. This is what you need to remember in joint hypothesis testing when we are doing. And joint hypothesis testing is done for multiple explanatory variables, slope coefficients hypothesis testing. Now here again the rules are exactly same. T stat is greater than T critical, reject the null, and your model is okay, fine. Okay, slopes are statistically significant. Then we have this particular part, like the confidence interval method, not very much tested in the examination. Again, you have to look for the same values, lower p value, and you reject the null. At least one of the slope is statistically significant. The correct word is at least one of the slope coefficient is not equal to 0 or statistically significant. Remember this. Okay. Then we have the joint hypothesis testing of two or more slope coefficients simultaneously. This is using the F distribution and F stat method. So again, you have to look for only this decision rule. Don't expect you will get question on F statistic or F stat calculation in the examination. Formula is slightly complex. Now here, if the F stat is greater than the T critical or the F critical value, then decision rule is reject the null. And this is applicable for the F distribution for joint hypothesis. Now next is regression diagnostics. In regression diagnostics, we got our model. Once we get our model, because the way assumptions are provided in the regression model, we can't trace those assumptions before forming model or before creating model. So all these assumptions are tested after creating a model, and all these assumptions needs to be tested. If there is violation of assumption, we have to think or correct those assumptions or those problems in the model. So first of all, we discussed about the explanatory variables are not perfectly linearly correlated. So the related concept in this particular chapter is multicollinearity. So we will see how this assumption is tested and how to correct those violations. Then next is the constant variance for all explanatory variables is tested with the help of heteroskedasticity. Then we have the no outliers in any of the explanatory variable measured using the Cook's measure, or related concept is Cook's measure. Remember, these are not the meanings. These are related concepts which are given in our book. Then the error term E is assumed to have mean 0 conditional on the explanatory variable. Like this. In examination, may get tested like that is conditional upon 0. Okay, which is covered in the omitted variable. Now, first of all, following assumptions are not tested and assumed prior construction in the model. So these assumptions are not tested. All the variables must have positive variance. Have you ever seen the negative variance? If you've seen it, just comment. Then random variables are assumed to be IID, independent and identically distributed. These two assumptions are assumed and you don't need to test, check, or like do whatever you want. Okay. Then we have the first, omitted variable bias and the extraneous variable bias. That is a bias variance trade-off. Now always remember, omitting variable is the problem and including unnecessary variables are the problem. So here we are discussing mainly like we are discussing what is omitted variable and extraneous variable. Omitted variable means variable was important but we dropped it. That is an omitted variable. Didn't consider that variable. Extraneous variable means the variable was not at all important but we included it in the model. Now if you do this, it does not affect the accuracy of the model. This is what you need to remember. Effect of extraneous variable, you have to also remember the like following conditions are satisfied and for the omitted variable, and then we have to also think about like what is the effect of omitted variable. Okay, so it has two effects. First, the included variables, if you are excluding important variable, then included variables will absorb the effect of the omitted variable. Okay, and then it will change the regression coefficient, and then it will also impact the residuals, and residual become predictor of the y. That's the problem. Now it should have like, to consider one particular variable as a omitted variable, you have to fulfill two conditions. So omitted variable is a correlated with the included variable first, then determinant of the dependent variable second. So if two conditions are satisfied, then we will call this as a omitted variable, important for theoretical standpoint or theoretical question. Effect of extraneous variable. So first of all, it does not affect the model and is not a very serious problem, but it increases the variable's explanatory power and declines or results into decline in adjusted R square. And when the true coefficient of added variable is 0, it increases the standard error in the model. So you will see standard error in the model, and then it will creates a problem in, this is a common problem in financial data where variables are high in correlation. So this is again the problem, extraneous variable. You have to understand it. Then bias variance trade-off. If you have the large model, this is what you need to remember. If you have the large model, the bias will be lower and the variance will be higher. If you have small models, so bias will be higher and variance will be lower. Then we have general to specific model and m-fold cross variable, m-fold cross validation model. So general, I will just give you the brief overview. Just read it out. What is given. Now GTS, the general to specific model. Build all the large model and keep dropping one variable at a time, which has the lowest explanatory power, like that. Okay. So based on the t-stat. So steps are very simple. Specify large model by including all the relevant variables. If some variables are statistically insignificant, focus on the word insignificant, remove that variable one at a time, then construct the model again. If you select the 100 variables for the model, then say 100th variable is not significant or insignificant, drop that variable and construct the model. Then repeat step 1 and 2 and keep repeating this and keep dropping one variable at a time until all the variables included in the model are statistically significant. Then we have second, m-fold cross validation. So m-fold cross validation, the process is very simple. Determine set of candidate models which are constructed using all the possible combination of variables. So you have to construct the multiple models, and then you have to split the data into m equal parts, estimate the parameter using m minus 1 of m blocks, and compute the residual using the parameters of excluded block. What is the meaning of this? Please watch it in the full video. It is not at all possible for me to explain. And you have to select the model with the smallest RSS. Then we have the heteroskedasticity. First of all, what is homoskedasticity? So skedasticity means variance and homo means constant variance. Hetero means not constant variance. Previously in 2019 there was a discussion of the conditional heteroskedasticity and the unconditional heteroskedasticity. So conditional heteroskedasticity means a variance of error term is changing according to the explanatory variable, meaning the variance of error term is related with x and we consider this as a problem. But if it is not changing according to x, this is homoskedasticity. Variance is not changing. Here, variance is changing. As the x is increasing, error term is increasing. The variance of error term is increasing. So this is the heteroskedasticity situation. Heteroskedasticity. The reverse is also possible. If the x is increasing, the variance of error term is decreasing. This is also heteroskedasticity. There is conditional heteroskedasticity, means the change in variance of error term is conditional upon x. If this is the case, this is the problem. If it is unconditional, error terms variance is changing, but there is no direct relationship with x. The change is not related with the x, then that is not the problem. Now this is what you need to remember. Effect of heteroskedasticity. The distribution of estimated parameters take a different form. Remember, consistency and unbiasedness are unaffected. Very important, and this is what you will get, this is the testing area of examination. Now detecting using the graphical method, which you already saw. So you have to create a residual plot and find out. Then what is the problem if there is a heteroskedasticity? Because of the heteroskedasticity, because heteroskedasticity does not affect the parameters, hence the fixes for the parameter is not required. However, the standard error is not reliable for the hypothesis testing. So we use the modified version of the standard error, which is known as, where is that? Okay. So white standard error is used. What you need to remember. Then approach to modeling heteroskedasticity. Approach 1, ignore. Approach 2, transform the data. Approach 2, transform the data before modeling. Approach 3, use weighted least squares, WLS, generalization of OLS. Okay, so for example purpose, you have to just understand what are the three approaches. Then we have the multicollinearity. Multicollinearity means the variables are perfectly correlated. The explanatory variables x1 and x2 or x1 and x3 or x2 and x3 are perfectly correlated, and this is our problem. Now how to identify multicollinearity in the model? By variance inflation factor. So you have to use this formula, VIF is equal to 1 divided by 1 minus rj square, where r square comes from the regression of x on the other model. So here This is very simple. You have to regress x with x, find out the r square, and then we have to use the VIF. If the value is about 10, this is considered as excessive, and if this is excessive, then we will consider two variables are correlated. Okay, solution to multicollinearity. Ignore the multicollinearity because this is not a technical problem in regression modeling. Identify the multicollinearity. This is the second solution. Identify the multicollinear variable and consider removing such variable. Very simple. Then residual plot visualization. Just understand it. Outlier identification is done with the Cook's measure. Here you have to remember this particular part. So Cook's measure B is greater than 1 indicates that the observation J has the large impact on the estimated model parameter, and there are outliers. So what you need to remember, this part is important here. Cook's measure is important here. Cook's is the distance measure is important, and this is used for the identification of the outlier. Now, which OLS is the best linear unbiased estimator? OLS. Which OLS is the best linear unbiased estimator? Simple. Ordinary least squares. In this particular case, we have to think about the linear unbiased estimator. First of all, what is estimator? Estimator is the one which estimates the population parameter using the sample data. So estimator part is clear. So here you have to only understand the meaning of this particular. PL. So is fine, best and linear. Now see, both alpha and beta are blue, best linear unbiased estimator. So these are unbiased estimators. There is no biasness. What is the meaning of unbiasedness? What is the meaning? Biased means, so your estimates or the estimates given by the estimator are able to predict the population parameter. Means the unbiasedness. So difference is lesser and lesser. This is unbiased. Best linear means out of all the methods available using which you can calculate the alpha and beta, if you use the OLS gives us the best alpha and beta which are in linear format. So best linear unbiased estimate. Okay, so best linear. But there is a possibility that there are best unbiased estimator, other unbiased estimators. Maybe those estimators will also be called as alpha and beta only, but using different models. But these are not linear. So if you consider all the linear estimators, so alpha and beta using OLS are the best linear unbiased estimators. If you consider all linear non-linear, then alpha and beta may not be the best. Okay, this is what you need to remember. The meaning of best linear unbiased estimator. Estimator's meaning is important. Best linear meaning is important. That is alpha, beta, OLS are linear measures. That's why we consider this as a best linear. And unbiased means the difference between the population parameter and the estimate given by the estimate is not there or lowest. Like, okay, so that's all about the 3 chapters revision. See you in the next chapter or see you in the next session. If you like this video, please tell me or if you have any suggestions. Thank you everyone.